So section 3.5, you should get a good start on it today. We are going to go back and grade section 3.4. I have that ready, but I just had you guys getting notes started while I was taking roll really quickly and getting copied out the door for their test. But as I was saying, as you're ready, section 3.5, we're taking today and Monday. We should finish most, if not all, of the notes today. Monday we'll be doing an extra example if we don't finish them all. But then I'll be taking questions from those of you guys that have gotten stuck on homework somewhere, because some of these do get really tricky. Just because they're basically word problems. With exponential and logs, that's been the entire chapter. You can really focus your attention this chapter on exponentials, on logarithms, on their rules, their properties, their graphs, their transformations, their domains and ranges. You can really focus your attention in this chapter. But section 3.5, the equations get a little messy with decimals and things like that, so you definitely want your calculator close. So once you have this down, if you have your calculator, go ahead and grab it out, get it open, get it warmed up, ready to go. We're going to use it a few different times today. But the calculator, hear me out, is not going to be enough, because you have to actually do some solving for variables that are stuck inside exponential or logarithmic equations. The calculator is just to help us get the decimal answers at the end from all of the work that we do to move things to other side of the second. So on Monday, I will take questions, and then if we have any extra time, it's a chapel day. But then you guys will have like somewhat of a work period to try to finish up, to go past where you got stuck in your homework. You can even start the review if you're caught up on your homework. And then Tuesday is the full review, going over questions that you might have on the review. Wednesday's the test. Okay? We already talked about how the test might have a calculator and a non-calculator part. Because for these types of problems, definitely want a calculator. So there might be like a third page or a last page that just has like the last few long answers. Multiple choice, you shouldn't need a calculator on, but the long answers, you might want a calculator. So the test will probably be in 2 parts, and we'll talk about that next week. All right, I think most of us should have this down. Let's go ahead and, just for sake of today, since you guys are already in your notes and to save on time, I'm actually going to have you guys, if you look at number 1, identify the proper model. I want you guys to really quickly underline model and underline equation. What it means by identify the proper model is to identify the proper equation. I'm going to go through right now and have you guys write down the different models that might be used in this homework. Just a quick word of the wise, we're only going to star a couple of them that you should actually memorize. The rest of them, it's just so that when homework says use this model or follow this model, that you know what it is or what the graph looks like. Homework's going to test you in a few different ways, but I'm not going to make you memorize all of them for the test. I'm not going to make you have to memorize all the graphs of all of them, but they are like super common equations that are used in, I don't know, one's in business, one's in finance, well, business and finance, same category. Some are in physics, some are in, do we get into chemistry? Yeah, we do, some radioactive decay. Some in chemistry, so they're just like commonly used formulas. You're going to see more in homework because they're just going to give you a formula and say, hey, guess what, this one's important too, and it has a log, or it has an ln, or it has an exponential. Logarithms and exponentials are used in all sorts of different equations and all sorts of different, not even branches of math, but even just fields of study. So we're just going to go through a few different big categories. Once again, only have to worry about memorizing the ones with stars, but they're all going to be helpful in homework. Let's go ahead and get them down in our notes. And then when we get to our first practice problem, we'll pause and go grade 3, 4, and then come back. So here's the first 2. Let me make these big. Guys, on the graphs, I will go ahead and show you an equation, but the point isn't to be super precise. It's just to have a quick sketch of what it looks like. Just to have an idea. That's all it is, okay? The graph is just to have an idea. If you're wondering, what's in that box, there it is. These formulas are 2 very common financial, compound interest financial formulas that involve growth. So they're just 2 special types. So the big category is exponential growth. The graph that they showed is y equals e to the x. I think you've actually maybe already seen these compound interest formulas, at least one of them. Remember I told you should star ones, or I was going to star ones that you should memorize? Out of all the ones you're going to see on the next few pages, for the test, you better star the 2 financial ones. You better star the 2 compound interest ones. And guys, once again, we're not filling in anything extra. You're just getting down the name, the basic equation, sketch of the graph. Just this one's special because he also has 2 very special, specific equations for compound interest that come under him. But no skipping of lines, nothing like that. Exponential decay, I don't really think there's anything under that. So it's just getting the equation and it's just getting the sketch of one example of exponential decay. Exponential growth goes up, exponential decay goes down. You're cheating. That's a good puzzle, I agree. I know, someone left it over there. Too much temptation. Yeah, Lainey.
What do the exponents say for the compound interest?
For the compound interest? We have up here, just in case it's too small, t times 1 plus r over n to the nt, and then this one is pert, p times e to the rt. Pert. P times e to the rt. Yeah, Chris? We have a lot of models and I'm about to switch the page. Do you think we can wait for a little bit?
Yeah.
Okay, let's wait until we start doing homework. Oh, what? You didn't have the models yet?
I just didn't have
Okay. Let's cut this a little while. Remember quick sketch? I'm going to skip over the examples. We'll just do those at the very end. We're going to get all of the models that we can. We will be back on this page for just a little bit once we start doing examples, so if you can at least leave enough room, that would help as well. We'll do 30 more seconds. Worst comes to worst, at least skip enough room. Okay, figure out how much room you need to skip. It's okay, we'll be back on this page. I'm going to go ahead and change in 5, 4, 3, 2, 1. Okay. We're just getting the models, don't worry. We'll go back and fill in the examples after the models. That'll be the end of our notes. So you don't need to skip any space. You don't need to skip any space. We'll just do all the examples at the end. Make this one a little bit bigger.
go, is it 2 over?
Oh, that's a good question.
Or is
That
it
looks
the
kind of
whole-
funny, right? Technically, according to PEMDAS, there's only really one way to do it, but it does look really weird. Think about the grouping of x minus b quantity squared. Since it shows then division by c, what it means is everybody over c, and it's all in the superscript. I'm not listening to you, sorry. Good question, I forgot that looks so funny. E is down as the base, and the whole exponent is the mess, negative x minus b. Sorry, negative quantity x minus b squared all over c. All in the exponent. Jacob?
When you would do that, do you distribute the negative into the x and the b?
After squaring. So PEMDAS, just view it this way, that's a negative 1 times, you gotta do the exponent first. You have to square this, and then bring in that little negative to everybody. AJ?
In the growth model, the denominator.
Denominator is 1 plus e, and e is to the power of negative 5x. Chris?
I think I lied about the U.
Okay, go. You didn't lie, it was just unreal. So 1 plus e to the negative 5x. 1 plus e to the negative 5x. If you guys notice, it has a horizontal asymptote. Here's the weird thing. A graph can have more than one horizontal asymptote. So to the right, it's getting closer and closer to this high horizontal asymptote, but to the left, it's getting closer and closer to 0. So that's maybe something you didn't realize before. I think this is the last one. Yep. Last one. Logarithmic. Which, to be honest, we've already seen these, so it's not really that crazy or that new. To be honest, I don't even know if you can draw both graphs. This one just has the common log of x, and this one just has the natural log of x. Natural log, his base is a little smaller. It's 2.71828. Common log 10, so he's going to be a little flatter. But we know how to deal with graphs, or at least we have it in our notes. So if you just want to do one of them, that's totally okay. Nice thing is we've already seen him this chapter, logarithmic models. And all the swoops are a little bit different, right? Exactly. Exponentials, if you're growing, it's swooping up really fast. If you're decaying, it's swooping down really fast. Logarithmic, it's going to be swooping up, but slower and slower. Logistic, it swoops up really fast, and then it goes and levels out and gets slower. Gaussian, bell curve, if you guys have ever heard of standard deviation, or statistics in general, the bell curve is used where it's like, okay, we're going, and then we're going back down.
Oh, it's like a roller coaster.
Yeah, kind of. And then which ones did I miss? We got Gaussian, we got logistic, we got exponential, decay and growth, and then logarithmic. I think we have them all. 1, 2, 3, 4, and 5. So once you guys have this one down, this is the last model. And remember, once again, I only starred the financial ones. The PERT, the continuously compounded interest, and then the P times 1 plus R over N all to the NT, N compoundings per year. However, there are some funny things that will show up in homework. So we are going to do some examples. We'll come back and talk about this page for just a second after we check our homework. So section 3.4. Oh, you don't need that. You need this. Section 3.4. Go ahead and put your pencil in your composition book. You don't need it because you're getting your colored pen. Let's go into our homework spirals. Not 3.5, 3.4. 3.4 was the culmination of all the work, the foundation that we laid, the basics that we tried to master on exponential and logs in sections 1 and 2 and 3. 3.4 was like, let's put it all together in these big old equations, and sometimes they're small, and sometimes they're big, where you need to solve for something stuck in an exponential or something stuck in a logarithm. We went over a lot of examples over 2 different days, but it does not mean that it was still, or that it was easy. Before we even start, does anybody have any odds they already know the other question on? As to how it was, what it was, Jacob?
55.
55? Anything else? You sure?
57.
Yeah. No, there were some hard ones, I totally agree. That's why I'm trying to give people a chance. Just 55 and 57? on the odds. Okay, you might come up with another one, but let's go ahead and go check the evens really fast and see which ones of those. I'm just gonna point to the answers. And if the answer is wrong, go ahead and mark it. Take a second if you can to check the work. But you can also ask even questions in just a moment. Number 2, that's the word we talked about in class, extraneous. Number 12, 10 to the power of, get rid of that log, you end up with 1 over 100 or 0.01. Both are totally fine. 1 over 100 I think is better, but that's okay. 3 to the power of both sides, you end up with 9. Once you know 9, you can plug back in order to get, or actually you know the y value is 2. They wanted the entire point, so they wanted not just 9, but what they told you y was, which was 2. Number 24, remember the book, like me, whoever made the answer key knew higher math and said we like ln better, so they used ln, but what other log could you have used? Log base 4. So one version of the answer is negative ln of 0.10 or negative ln of 1/10 all over 3 ln of 4 or ln of 4 cubed 64. But you guys could have had negative 1/3 log base 4 of 0.10. The decimals would have matched. That's why you have to get the decimal, because it might not look the same. Okay, so on the test, if there was like one of these really tricky ones, and if your answer wasn't written exactly the same way in the answer choices, what could you do to your answer? Get a decimal, and then compare the decimals of the answers. Now, there aren't tons of these really hard ones, but couldn't that be a way of making it match, even if it doesn't look the same? So decimal 0.554. But the proper answer, the best answer, would have been written with a log, just maybe you had a different log. Instead of ln's, you might have had log base 4. This one, hopefully, though, you used an ln. It's the easiest way to go. Get rid of that e. One way could have been ln of 3 over 40 all over negative 4. They like to write that all over negative 4 as a coefficient of negative 1 over 4. They'd multiply by the reciprocal. But you could have done all over negative 4, but the decimal should have been the same, 0.64. As you guys are checking that decimal, let me go ahead and scroll to number 36. We actually had one kind of like this in our notes, actually a lot like this in our notes. Was it this exact problem? Maybe not. But an ln is a great idea, cancel out the e, just this one stuck. Oh well, bring down, solve. Final answer, 0.181. That looks so familiar, I'm almost positive we did that one in our notes. Right? It looks super familiar. I think we did it in our notes. 0.181. Number 15. He was easy and yet hard all at the same time. He was easy and yet hard all at the same time. The honors kids got stumped on this one a bit. Not in homework, like when it was fresh in their mind, but on a test there was one kind of like it. Ooh, maybe you're starring it as we speak, but just saying there was one like it. You guys have different tests, but coming back. You have to get rid of the ln, so e to that is a great idea. But did anybody really cool happen to deal with the square root before taking an e?
Yeah.
Yeah, Lainey, what'd you do?
I used an exponent of 100.
I actually think the easiest way to go would have been to say, because we've worked on this a lot, guys, a square root is a 1/2 power, right? Why is that cool? If you have a power in an ln, what can you do?
Cancel.
How? Okay, there you go. Move it to the front, then you gotta get rid of it. So if I have 1/2 ln of x minus 8, how can I get rid of the 1/2? Divide by 1/2 or multiply by the reciprocal. So we could just multiply by 2 over 1, right? Well, that's just gonna be 10. Hey look, how easy is this?
Oh, so easy.
Just gotta take e to both sides and then add 8. E to both sides and then just add 8. That's nothing. It was a little tricky when you left the square root in, which still was legal. That's what the book did. Fine, they were doing it the hard way. Does anybody see, because this is where it gets tricky, they didn't show the work. How'd they get from this one to that one? What'd they do to both sides?
Both sides. They don't get full credit.
Well, they did get it right though. And they made a good mental jump for their capabilities. But for you guys, most of you need to see that they square both sides. So then what happens with the square root of the squared? Cancels, x minus 8 is left. How do I raise a power to a power? But some of you are like, that's trickier than just getting the 1/2 power in front and moving them to the other side. And I agree. I agree. Not impossible, just trickier. I think these are the last two. Oh, no, number 84 is the last one. Okay, we'll get to number 84 in a second, but first of all, let's get to numbers 60 and 78. Careful on number 60. Did you catch the extraneous one? You have to take both, test them in the logs and say, is it okay? Is it log of a positive? The 2, that's positive, that's positive, that's positive. Woo, the 2 is good, keep them. Plug in the negative 3 though, that's positive, good. That's negative and that's negative. If there's at least one that goes negative inside a log, it's extraneous. So negative 3 is a no, 2 is a yes. I've used some properties, kind of like the last example we did in our notes. Number 78, the final answer, E is the best, but I guess you could put 2.718, but yeah. E is the best. And then last but not least, number 84. 84 kind of gets you ready for today, and here's why. It gives you a kind of nasty equation that has some sort of real-life application. This has to do with demand for phones or something, right? Yeah. Gives you a nasty equation. If you guys look at this according to your notes, it's actually a logistic curve. Interesting. We're coming back. It's a nasty equation, but what they did is they said, okay, cool, we're just going to give you a variable. You say, all right, let's plug and chug. And then they say solve for the other one. But you had to read the problem to figure out that when they said P is 169, that meant the demand. Oh, no, it's price. Never mind. That meant the price, so it got plugged into the P spot. And then when they asked for demand, you had to read the problem where they said, oh, hey, by the way, X is demand. So we have to solve for this little guy. And there are lots of different ways. It's okay to get decimals as long as you leave more decimals than you need at the end. Because if you round right away to the super smaller answer, like to the 3 decimal places I tell you to do, then you're going to have, as you keep on rounding and keep on using rounded, you're going to have all this error that comes in. So you want a lot of decimals. If you can keep it like a full one, the full number with all the decimals, it's even better. But at least have 1 more or 2 more past the 3 I tell you when it's not the final answer. But they go dividing by 5,000, they go subtracting the 1, then hopefully you guys know undo the division, even though it's yucky, get it up there. So they undo the division, then they bring this one and divide it over to get another decimal. Then they subtract the 4, they ln both sides, they divide by negative 0.002, and they end up with 983 approximately. Depending on how you rounded your decimals. If you had a lot of decimals earlier in the problem, you might have a little bit different number, but it should be really stinking close. If you do what I tell you to and have at least 4, if not more, decimals the whole time. Okay? But this is an example where the math isn't any different. Just the numbers are gross. But the math isn't any different. Eventually you get to a place where you isolated the exponential like you were supposed to do. Isolate. And how do you get rid of e? ln both sides. ln of e cancels, ln of this side stays, and then go, go, go. Okay, b. Same exact thing, just plug in a different number and solve, solve, solve. Now they're saying, what if the price is $2.99? Which, for you, you're like, ugh, all this math. But for them, they're like, no, we're curious because, okay, there's a bit of a difference between the price being $169 and the demand being 983 phones, and the price being higher, quite a bit higher, $299, and the demand is 684 phones. What could they do with that information? Price is $169, you have 683. When it wasn't 683, what was it? 983. Couldn't they multiply the demand by the price and figure out how much money they would make if the price is $169? And then what could they do down here? Multiply 684 times $299. What are they trying to figure out? They just want to make money. They don't care if it's cheap for you or not, right? You guys know retailers and wholesalers and all that, like all these different, whether it's with phones, whether it's with accessories, whether it's with clothing. They just care about the money, most of them. They don't care whether it's easier or harder for you to buy, they just wanna make more money, so they're like, okay, can we jack the price up and still make more money? Alright. Kiddos, that's the end of homework. Are there any evens that we got stuck on along the way? Besides the final word problem, because we're gonna work on this skill today as we do some more real life problems. They're just kind of messy. Anything besides number 84?
Number 16.
Okay. So let's start with number 16. And then we'll go to the 15 ones that Jacob had a question on. Number 16 was kind of funny because they gave you a graph. So the information it gave you was definitely a bit different. I'm going to see if I can just do it in the page because there's a lot of space around this one. It says, basically, find the intersection point. Intersection point where they both hit. Guys, what do we do with two equations in order to solve for the intersection? Yeah, I guess we could plug in 2 as the y value because we know that if that y equals 2, but usually the easier way of saying it is just take f, take g, and say, hey, they have to be the same somewhere. Where are they the same? At the point they share. So we take f, who is log base 3 of x, set it equal to g. Every time intersection, set the equations equal. That's from algebra 1. And cool kids, the math, how do we undo log base 3?
Power of 3.
Good. Then that cancels. What do we have left?
6.
Uh-huh. But 9 is the x value, they want the point. So 9 is the x, and what was the y that was given? 2. So take the x and then take the y.
That was a weird thing.
Yeah. But the graph and the pictures made it funny. But it's an intersection, so set them equal. Then do 3 to the power of x is 9, y is 2. Then you had a couple questions on the 50s. 55, I think, and 57. Okay, let me get rid of that real quick. Okay. If you guys don't have a question, that means you got it, so help me out. What'd you do? What'd you see on 55? 7.
I put ln
55.
x over x plus 1.
Okay, so Jacob said quotient property, and I totally agree. X over x plus 1. You gotta condense before you can do anything. Can't use 1 to 1 because there's that 2 over there. Just like the one we did yesterday. Everybody, look at that problem, and whether or not you're seeing it for the first time, because you don't even remember what you did last night. How do you get rid of ln? Yeah. So throw in an e, throw in an e. That's gone. Come on, cool kids, we worked on this a lot. How do we? There are x's in 2 spaces. Who cares? What do we do next?
Multiply by the denominator.
Get the operation simpler. Undo the division. Okay. Now, the x is still in 2 places and it's still stuck, but at least it's not stuck in a denominator. Now it's stuck inside, a multiplication. What do you think we're going to do?
Distribute.
Get him out of there. The only way to do it legally is distribute. Now help. Your turn. What was this all for? What are we supposed to do?
X.
What about the x?
Solve for.
How?
Okay,
No, it's good. We're solving for it, but how?
Oh, the distribute.
Yeah. The distributive property we're going to factor it, but we can't factor it until we get it all on.
one side.
Get the x's on the left, right? We already have this one. Subtract the other one. Leave him. He doesn't have an x. Now what can we do? And what's left? Divide by x, 1, not 0. Divide by x, e squared. And all of that was 2. Oh, nice. Get him by himself by doing one simple division. If I divide, that cancels. X equals e squared over 1 minus e squared. Did you get it?
Yes.
57.
Oh, you missed your spot. You're distracted.
57. Do I have a property? I have a quotient, yeah? I do have a quotient. So I can say ln of x plus 5. Guys, you tell me.
ln minus x minus 1 over x plus 1.
Now what property can I use? Or what can I do to both sides? Finally, distract me. Up here. Multiply.
No.
What do you mean e to the power? Good, e to the power. Now,
Easy.
Everybody freak out, there's X's in 3 places.
Oh,
Okay, we got that, because, who cares? What are we gonna get rid of?
X minus 1.
Yeah, get rid of the division, simplify the operations if nothing else. What happens, when we put an X plus 1?
Oh,
But that's okay, we did the multiplication a second ago, whatever, do what you gotta do. Get the X's out of here by foiling. So X squared, anybody mental math? Plus?
Oh, this.
Oh. What are we gonna do? It's a quadratic. Factor after we get everything to one side. Gotta get it equal to 0. So I subtract an x, that'll be 5x. I add a 1, that'll be 6. And hopefully at this point you guys know how to factor to be x plus 2 times x plus 3. And now when we got rid of these guys, we have a 0. How do we solve for the zeros?
Negative 2 and negative 3.
Negative 2 and
Negative 3.
extraneous. Plug in a negative 2. That's positive. Ooh. Negative 2, that's a negative, right?
Yes.
A negative 2, that's a negative?
Yeah.
Is that bad?
Yep.
Are there 2 extremes?
What about negative 3? That's good. Positive.
Negative bad.
What was the back of the book for 57?
No solution, extraneous, no solution.
Because both of them, when plugged in, were illegal.
Where's illegal?
But if this was a long answer on the test, you wouldn't get any credit if you just left it blank, because you didn't show me that you knew they were illegal. If you got all the way there and said illegal, nicely done. All right, 3-5. This is all in the video. If you guys need to hear that explanation slower, you can slow me down. 1.5 speed? Not 1.5, 0.5.
One question on the last problem. You said since one of them didn't work, that means all of them don't work?
No. One of them didn't work. I went to go check the other one. It didn't work also.
Okay.
So I eliminated both of them, showed them both as illegal. Otherwise, if one worked, it would have. All right, here we go. We have all these models, but kiddos, for using the ones that are starred, we're just going to label a couple of the variables really quick, okay? For financial stuff, or actually just kind of in general for